Welcome to Selection with Sathi. Today we will master tries, also known as prefix trees, with code on screen. A trie is a tree-like data structure that stores strings character by character. We will cover the trie structure, insert, search, delete, prefix counting and autocomplete. This topic is important for GATE CSE, placements, and coding interviews. Let us begin. Let us start with the trie structure. Look at lines 1 through 5. Each trie node has 3 fields. Line 3, children, is a dictionary mapping each character to a child trie node. Line 4, end is a boolean that marks whether this node completes a word. Line 5, prefix count, tracks how many words pass through this node. The trie itself, on lines 7 to 9, simply holds a root node. The key insight is that the path from root to any node spells out a prefix. Words sharing the same prefix share the same path. For example, cat, car, and card all share the path C, A. Inserting a word into the trie is straightforward. Look at line 2, we start at the root. Line 3, for each character in the word, we do 2 things. Lines 4 and 5, if the character is not already a child, create a new trie node for it. Line 6, move to that child node. Line 7, increment the prefix count at each node we visit. This tracks how many words pass through this node. Line 8, after processing all characters, mark the last node as is end equals true. The time complexity is O of L, where L is the length of the word. Each character requires at most one new node creation. Searching for a word is similar to insert but without creating nodes. Look at lines 3 through 5. For each character, check if it exists as a child. If any character is missing, the word is not in the trie. Return false. Line 6, move to the child node. Line 7, after traversing all characters, check is end. If end is true, the exact word exists. If false, only the prefix exists. For example, if we inserted car, searching for CA would return false because the nodes end is not set. The starts with function on lines 9 to 15 is simpler. It just checks if the prefix path exists, without checking end. Deleting a word from a trie requires careful handling. Look at the recursive delete function. Lines 3 to 7, when depth equals the word length, we have reached the end node. Line 6, unmark is end. Line 7, return true if this node has no children, meaning it can be deleted. Lines 8 through 11, recursively descend to the end of the word. Lines 12 through 16, on the way back, if the child should be deleted, remove it from the children dictionary. But only delete if the current node is not the end of another word and has no other children. This ensures we do not break words that share a prefix with the deleted word. Time complexity is O of L. Prefix count is a powerful feature of tries. Look at lines 3 through 6, navigate to the prefix endpoint, character by character. If any character is missing, return 0. Line 7, return the prefix count stored at that node. Because we increment prefix count during every insert, this value tells us exactly how many words pass through this node. Lines 10 through 14 show examples. After inserting cat, car, and card, count prefix of CA returns 3 and count prefix of car returns 2. This is O of L time, where L is the prefix length. No need to traverse all descendants to count them.
Let us trace inserting cat, car, and card step by step. Insert cat. Start at root. C is not a child, create it. Move to C, A is not a child, create it. Move to A, T is not a child, create it. Mark T as end. Prefix counts, C is 1, A is 1, T is 1. Insert car. Start at root. C already exists, move to C, A already exists, move to A, R is not a child, create it. Mark R as end. Prefix counts, C is now 2, A is now 2, R is 1. Insert card. C exists, A exists, R exists, D does not exist, create it. Mark D as end. Prefix counts, C is 3, A is 3, R is 2, D is 1. Notice how C and A are shared by all three words. Let us search for car in the trie. Line 2. Start at root. First character C, line 4, C is in root's children. Line 6, move to C. Second character A is in C's children. Move to A. Third character R is in A's children. Move to R, line 7, check our dot is end. It is true because we inserted car. Return true. Word found. Now what if we searched for CA? We would reach node A after 2 characters. But a dot is end is false. So search would return false. The prefix CA exists, but it is not a complete word. Prefix matching with CA. Navigate to the node for prefix CA, route to C2A, check A's prefix count, it is 3. That tells us 3 words share the prefix CA, cat, car, and card. Now check prefix car, navigate route to C2A to our RS prefix count is 2. 2 words share prefix car and card. What about prefix D? D is not in root's children, so count prefix returns 0. This is incredibly fast, just O of L per query. Compare this to scanning through an entire dictionary. Let us delete car from the trie that contains cat, car, and card. We descend, route to C2A to R, depth equals 3 which equals the length of car. Unmark is end at R, now our dot is end is false. Does R have children? Yes, it has child D for the word card. So we cannot delete node R, return false to the parent. No nodes get deleted anywhere on the backtrack path. The trie now has cat and card but not car. If we search for car now, we reach R but our dot is end is false. Search correctly returns false. But card still works because our 2D path is intact with D dot is end true. Autocomplete is one of the most practical trie applications. We have cat, car, card, cap, cape in the trie. User type CA. We navigate to the node under C. Now we do a DFS from this node to find all complete words. Branch T, T dot is end is true. Add cat. Branch R, R dot is end is true. Add car. Then R has child D with is end true. Add card. Branch P, P dot is end is true. Add cap. Then P has child E with is end true. Add cape. We found 5 suggestions: cat, car, card, cap, cape. The DFS explores only the subtree under the prefix. This is exactly how search engines and phone keyboards suggest completions.
Quick exam tips. First, tries use more space than hash tables because each character gets its own node. But they give prefix-based queries for free, which hash tables cannot do. Second, a compressed trie or radix tree merges single-child chains into one node, saving space. Third, key applications include spell check, autocomplete, IP routing, and T9 predictive text. Fourth, for gate, inserting n words of average length L takes O of n times L time. Space is O of sigma times n, where sigma is alphabet size and n is total nodes. For more DSA concept videos with code on screen, download the Selection with Sathi app. Like and subscribe. Thank you.